Good morning, students. Once again, I welcome you all for this session. Today, we will going to start with another design, that is design of flanged beams. Okay, so nothing but T beams or L beams. So in the analysis also, we have seen that what you mean by flanged beams or T beams. So T beams are nothing but the beams in which slab and beam. See, this is the slab, okay, and this is the beam. Slab and beam are casted simultaneously. Okay, they will going to act as a single unit. Okay, while casting, while putting the concrete, okay, the concrete will be poured simultaneously, slab as well as in the beam. So such beams are known as flanged beams or T beams. Okay, normally if you see, there are number of beams. This is 1, 2, 3, 4. Okay, and whatever you are seeing this top, it is nothing but the slab. So slab and beams are casted simultaneously, then such a system is called as flanged beams system, or it is called as T beam. Intermediate beams are called as T beams, and end beams, see this beam and this beam, so these are called as L beams. Okay, end beams are known as L beams and intermediate beams are called as T beams. Then what is the design of T beam? How the T beam will be designed? Almost the design will be same as that of singly reinforced beam, what we have seen in the previous classes. Okay, so whatever the changes we are going to see. So in most of the cases, okay, this is the practice. Okay, slab and beams are casted simultaneously. So normally in all cases the beams what we are seeing are T beams. Okay, because slab and beams act together as a single unit. Okay, so some of the things you have to remember already we know in the analysis. Okay, so one is effective width of flange, that is called as BF. This now see, this is a continuous slab and this beam over the beam slab will be continuous. Now what are the elements of this T beam? Now if you design this or this, any one beam you have to design. So if you consider this beam, okay, how much slab portion we have to consider? So this is nothing but BF. BF, F means flange. So this is the flange, okay, and this portion is web or rib. Okay, so this length is indicated as BF, breadth of flange. This is BW, and overall depth of the beam it is considered, even though it is slab is there, this slab depth plus this beam depth is overall depth of this T beam. So from top of slab to the bottom of beam, this total depth is called as depth of the T beam. Okay, now so this is width of web or rib, this is depth of flange. Depth of flange means depth of slab. This is width of flange, BF. Okay, remember BF, DF, BW. Okay. So next, what is the effective width of flange? How much this BF we have to take? In the design, they will not going to give this. Okay, in the problem, so we have to calculate this. Okay, so in the beginning you have to assume this. Okay, the effective width of flange should in no case be greater than the breadth of web plus half the sum of the clear distances to the adjacent beam on either side. Now see in figure. Now what is the load on this beam now? So over this beam slab is there. So half of this portion, half of this slab and half portion of this slab load will come to this beam. So half means this span. Half of this span plus half of this span will be the total width of flange, that is BF. Okay, half of this span plus half of this span will be the width of BF, that is breadth of flange. Okay, next, as per the code suggests that, right, for T beams. Okay, so when there are number of beams, okay, so how much you have to consider this BF? So for that you have to go to the page number 37. Okay, IS 456 2000 code book. So go to the IS 456 2000 page number 37. Okay, so there will be a equation, that equation will going to use to find out the BF, that is breadth of flange. So for T beams, this BF is equal to L0 upon 6 plus BW plus 6 into DF. Don't add this, okay? So it is there in code book in page number 37. So using this equation, we can find out this BF. Okay. So then what are the, if it is L beams, if you are designing end beams are considered as L shape, that is L beams. So for L beams, this BF, see this BF will be calculated using this equation. Both the equations are there in IS 456-2000 page number 37. Okay. Then what are these terms? So BF is nothing but width of flange. Okay. Then BW, width of web or rib. Then DF is depth of flange. F means flange here. Width of flange, depth of flange. BW means web, width of web or rib. Okay. So BF is effective width of flange. Then L0, what is this L0? L0 is nothing but distance between the points of zero moments in the beam. So points of zero moments, where the moment will be zero in the beam. So at the two supports. Now sir, this beam is resting on two supports. If you see the length of this beam, like this, not this is the length. Okay, length of beam. This beam will be resting on two supports. This is one support here, another support at the other end. So the distance between center of supports is nothing but L0. Okay, yeah. Or you can say that it is the effective span for simply supported beam. So distance between center of support to the center of support is nothing but L or L0. Okay, that L0 you have to substitute here. Then BW is known. DF is depth of flange or depth of slab. This is width of flange you have to calculate. Okay, so this is one important factor you have to remember, that is there in page number 37. Okay, next effective depth. Okay, effective depth of the beam, T beam. Now again from top of the slab to the center of reinforcement, somewhere here reinforcement will be provided, tension steel. So from top to the center of reinforcement is effective depth of the beam. Then width of web, BW we know. Then flange thickness, DF is nothing but the slab thickness. Then these are the minimum reinforcement required. Okay, already we know. So when you start this problem, automatically we are going to get the clear picture of this. So now let us start with one design problem. We'll take a T-beam design. Okay, the problem is like this. Okay, a T-beam slab floor of an office consisting of slab 150 mm thick, spanning between ribs or webs spaced at 3 meters centers. The effective span of the beam is 8 meter. Okay, the effective span of the beam is 8 meter. Live load on the floor is 4 kilonewton per meter square. Using M20 grade concrete and Fe415 HOST bars, design one of the intermediate T-beam. Okay, so only one beam you have to design. Now there are a number of beams here. So this is the office building. Over the building top, slab will be provided. Okay, and this slab is resting on the number of beams. So this beam and this beam is T-beam, and these two beams are L beams. But what they asked, design a T-beam, any one, either this beam or this beam you will going to design as a T-beam. Okay, as per the given data, okay, this is the slab, what we are seeing, this small rectangle, this is the slab, and below the slab this is the beam. So both slab and beam including this is T-beam. Okay, and we know that what are the elements of this T-beam. This is the breadth of flange BF, and this is the DF, and this is BW. Okay, so as once again I will read out the problem. A T-beam consisting of slab 150 mm thick. So this slab thickness is 150 mm, spanning between ribs. So this slab is spanning between ribs. The ribs means this webs. This is web of the beam. This is web of T-beam. So this slab will be resting between these beams, okay, spaced at 3 meter center. So these beams, this is one beam, this is end beam, this is another beam, this is L beam. So the distance between center of one beam to the center of one beam is 3 meter. Try to understand, this is important. Okay, so the slab is resting in between ribs, and these ribs or beams are spaced at 3 meter. See, from center of this beam to the center of this beam is 3 meter. From here to center of this is 3 meter. Okay, the effective span of the beam is 8 meter. Okay, here you cannot see the span. So span is length. Now this is one beam. Length of this beam, like this, I will take this. Length of beam is, or span of the beam is 8 meter. So here below this support is there, column is there. Here column is there. At the other ends also columns are there. So the distance between one support to the another support is span, that is 8 meter. So lengthwise if you see, it is 8 meter. These beams are spaced at 3 meters. Okay, the live load on the floor. Floor means over the slab. Okay, the load on the slab is 4 kilonewton per meter square. Okay, right. So using M20 grade concrete and Fe415 grade steel, you have to design any one of the intermediate T beam, this beam or this beam. Okay, so let us write down the given data. Effective span L 8 meter, that is lengthwise it is 8 meters effective span, small l. Depth of flange, this is a flange, depth of flange DF or slab thickness 150, it is given 150 mm. Then live load 4 kilonewton per meter square. Okay, spacing of T beams, see, center of this beam to the center of this beam is spacing of T beam, that is 3 meter. Then FCK 20 Newton per mm square, Fy is 415 Newton per mm square. Now as usual, the first step is you have to find out the cross sectional dimensions, that is width of beam BW, right, effective depth small d, and overall depth capital D. So as usual, we are going to take effective span by effective depth ratio. Okay, so what is the effective span by effective depth ratio for simply supported beam? Already we know that 20. It is a simply supported T beam. So span by depth ratio will be 20, that is L by D is equal to 20. But for T beams, okay, but for T beams, this ratio, that effect span by depth ratio should be multiplied with the modification factor. Okay, that we're going to see. Now normally this will be assumed. In the previous problems also we have assumed this is width of the beam. So width of beam or width of web we can assume 300, 250 mm, 300 you can assume any value. So this BW will be 300 mm. Then flange width BF. Now this BF, initially we have to take this BF is equal to 3 meter. How it is 3 meter? See, so for this beam, what is the load? Slab load. Half of this slab, this is one slab, half of this slab and half of this slab load will come to this. Half means here to here, half means it is 1.5, and from this side it is 1.5. So 1.5 plus 1.5, it is 3 meter. Okay, this is nothing but one span you have to consider. BF is equal to 3 meter. So this BF is 3 meter. Half this side, half this side. So BW is, we have assumed 300 mm. This BF you have given in the problem, it is 3 meter. Okay. Now, if you go to that page number 39, okay, go to page number 39 and refer figure number 6. Okay, figure number 6, IS 456 2000. So there one chart will be there. Okay, that is referring figure number 6, modification factor KF. In the deflection calculation we have used this. Okay, that is KT, KC and KF value. So since it is a T beam, KF comes into picture. So if you refer figure number 6 and you calculate this BW by BF ratio, in that figure x-axis is what? X-axis will be BW by BF. So BW 300 mm, this width of web we assume 300 mm, BF this is 3 meter means 3000 mm. So this ratio BW by BF 0.1. So for this ratio 0.1 BW by BF ratio, the KF value is 0.8. Refer that figure number 6. Okay. So for this span by depth ratio, we have to multiply 20 into this KF. Okay. So therefore, span by depth ratio for this T beam is equal to 20 into KF. That is, span is 8000 or 8 meter, 8000 mm divided by D. We have to find out. That is equal to 20 into KF is 0.8. So therefore, effective depth is equal to 8000 divided by 20 into 0.8. This comes out as 500 mm. So remember, what is the change here in this first step? This already we know for simply supported beam, right? Basic span by depth ratio is 20. So for this 20, we have to multiply 0.8. How this 0.8 we have got? Go to page number 39, figure number 6. Calculate this ratio. For this ratio, this KF value is 0.8. So this 0.8 is multiplied with 20. If it is T beam, then now we'll get effective depth D is equal to 500 mm. So this is small d. So for capital D, we have to add 50 mm effective cover. So directly you can add 50 mm to this, we'll get capital D. So overall depth capital D is equal to 500 plus 50, that is 550 mm will be the overall depth. So finally you can write down what are the dimensions of T beam now. Width of web or rib is 300 mm, effective depth will be 500 mm and overall depth will be 550 mm. So this will be the first step of design of T beam. Okay, so once the dimensions are fixed, now we can calculate the loads. Okay, the total loads on the beam. So over the beam, what is there? So the slab will be there. Now see here, this beam, over the beam, the slab load will be there, or slab will be there. The slab load we have to consider now. In the previous case, only the beam was there. We have taken self weight of the beam, live load of the beam. But here, slab load also we have to consider over this beam. So what is the length of the slab now? BF. Okay. What is the depth of the slab? DF. Okay. So BF into DF. Okay. Into 25. BF into DF is what? Okay. It is cross sectional area of the slab and you multiply by 25. Now see, self weight of the slab. Okay. So 0.15. What is 0.15? It is the thickness of the slab, 150 mm. So 0.15 into 3 into 25. Now see, this slab we have to consider, this slab load we have to consider. So what is the thickness? It is 150 means 0.15 into 3 meter. Okay, BF is 3 meter. 0.15 into 3 meter into 25. Okay, so 25 is what? It is the density of RCC. So this will give self weight of the slab, that is 11.25 kilonewton per meter. Okay, then floor finish. So over this slab, now suppose over this slab, one more floor, if you consider one more floor is there. So over this slab, what we're going to put? We're going to put the tiles. Okay, that floor tiles or anything you can take as a floor finish load. So roughly it is assumed. Okay, it is not given. Even if you don't consider this, fine, no problem. But floor finish 0.5 to 0.6 you have to consider. Again 0.5 or 0.6 into 3 meter. Again this 3. So for this area we are considering the slab. So over this slab we are putting the tiles. Okay, the tile thickness, what you can say, that 0.6 to 0.5 into 3 meter. That is the floor finish. Then self weight of rib. We have considered this slab and floor finish. Next is this beam or web. Okay. So self weight of the rib. So what is the dimension of the rib now? This is BW. Okay, this is BW. What is the depth of beam now? Only beam, because we already consider this slab. Okay, so only we have to consider this beam. Okay, so BW into this height. Now we know the total depth of the beam, T beam. Total depth, okay, from here to bottom, capital D. Capital D minus this slab thickness will give height of this only beam. Okay, now see here. So self weight of the beam or rib or web is equal to 0.3, that is width of beam. 300 mm means 0.3 meter. Okay, then this is 0.4 or 400 mm. How we have got 400? Now see, we want only this height. Total height is capital D. So capital D minus this 150. Okay, that is 550 minus 150, 400 mm. This only this. So 400 means 0.4. So 0.3, 0.4 into 25 density of RCC. This gives 3. Even plaster will going to apply for this. Plastering will going to do. So that plaster finish also you have to consider 0.5, 0.45 to 0.5. So 0.45 to 0.5. So that is 0.45 kilonewton per. So add all this. This is a total dead load. Okay, that is dead load of the slab plus floor finish, then dead load of this rib and plaster. So add all this. This is a total dead load, that is 16.5. Then live load it is given in the problem. Okay, live load it is 4 kilonewton per meter square. Okay, it is 4 kilonewton per meter. Actually it is 1 meter we are designing this. So 4 directly you can write down 4. So add this 16.5 plus 4, that is dead load plus live load. The total working load small w is equal to 20.5 kilonewton per meter. This is W, not WU, working load it is, or service load. So multiply 1.5, will get factored load. WU is equal to 20.5 into 1.5 factor. So we'll get now WU. So this is the total load which will be coming on this T beam. Okay. Now once the load is calculated, next important step is calculation of bending moment and shear force. So there is no change here. Okay, whatever the steps we have followed in the singly reinforced beam or doubly reinforced beam, it will be same. So we will going to calculate maximum bending moment and maximum shear force. So maximum bending moment mu is equal to WL square by 8. Simply supported it is. So it is WL square by 8. So WU it is 30.75 L. Okay, span, not this span. So lengthwise span of the beam is 8 meter. Okay, WU into L square, 8 square divided by 8. So 246 kilonewton meter. So we have substituted in meter. So 246 kilonewton meter. Then what is shear force? It is a VU. Factored shear force VU is equal to WL by 2. This is WL square by 8 bending moment. This is WL by 2. That is WUL by 2. WU 30.75 into L 8 divided by 2. It is 123 kilonewton. So this is maximum bending moment at center. This is maximum shear force at supports. Okay. So once the bending moment and shear force are calculated, now actual effective width of flange we are going to consider. Now in the beginning we have taken as 3 meter now. This we have taken as 3 meter, but as per the code we are going to consider. What code says? Again go back to the page number 37. Okay, IS 456 2000. Page number 37, IS 456 2000. Okay, so this is the equation. So breadth of flange is equal to L0 upon 6 plus BW plus 6 into DF. This is the formula. Okay, width of flange, effective width of flange BF is equal to L0 upon 6 plus BW plus 6 into DF. So L0 is nothing but L, span. Okay, it is 8 meter divided by 6. BW 300 mm means 0.3 meter plus 6 into DF is depth of flange 0.15 slab thickness. Okay, so this we're going to get 2.53 meter or 2530 mm. Okay, this is one width, one effective width of the flange, and another what we have taken? We have taken as 3 meter. It is given in the problem 3 meter. Out of these two, whichever is least, okay, whichever is least, that we have to consider. Now this is, you can calculate this also, nothing but, so this is center to center is 3 meter, okay, and from inner to inner edge of the beam is how much? So this is 3, center to center is 3 minus half of this minus half of this, okay, that is 3 minus 0.15, this will going to get 3 minus 0.3, that is another, that is 2.7. So out of these two, okay, out of this and this, whatever is the least value, that will be the final BF value. Okay, here in this case this is the less, right? So effective width of flange is equal to 2530. Suppose this comes lesser than this, in case if this value is lesser than this, consider this as the effective width of flange, that is BF, but here it is smaller, so BF is equal to 2530 mm. Now next, so once this step is over, next area of tension reinforcement, as usual EST we have to calculate. Okay, so first percentage calculation, that is PT, as usual this formula 50 into bracket 1 minus under the root of 1 minus 4.6 mu upon FCK BD square Fy upon FCK. So substitute all the values, 50 into 1 minus under the root 1 minus 4.6 mu, okay, that is 246 kilonewton, multiply 10 raised to 6 Newton mm divided by FCK is 20 B. Now see, important here, what I have written here, here you have to substitute this B is equal to BF, what you have calculated here, BF. This BF you have to substitute here. Okay, so BF is not this width, not this BF, BW. So this will be this BF, width of the flange, effective width of the flange, this BF you have to substitute. So it is 2530 into depth of, effective depth is 500 mm square divided by FCK, that is Fy upon FCK. So the percentage comes out 0.94%. Okay, the percentage of steel 0.94, but we want area. Area of steel is equal to what? AST is equal to percentage divided by 100, that is PT divided by 100 into, as usual formula, PT by 100 B into D. So PT by 100, now B is this BW. Okay, here you have to substitute BF, here you have to substitute BW. So width of web, that is BW into D, same formula, that is PT by 100 B, in the previous case we have taken PT by 100 B into D. Now here B is BW here, so PT by 100 BW into D. So 0.94 divided by 100, BW is 300, this is 300 into 500 effective depth. So area of steel is 1410 mm square, 1410 mm square. Now area we have got, now we have to find out the number of bars. So for that you have to assume the bar diameter. So you can assume 16 mm diameter, 18 mm diameter, 20 mm diameter, 22 mm or 25 mm diameter. So let us assume 25 mm diameter. If you assume higher diameter, number of bars will be less. Okay, so assuming 25 mm diameter, what is the number of bars? AST upon, that is total AST divided by area of 1 bar. So total AST is 1410 divided by pi by 4 D square, diameter 25 we are assuming, 25 square. So 3 numbers. So the main steel, that is at the bottom of the beam, what is main, how many numbers? 3 numbers we have to require. So therefore provide 3 bars of 25 mm diameter as a main steel at bottom of the beam. Okay, so at the bottom of the beam we have to provide 3 bars of 25 mm diameter as a main steel. Okay, so how much actually we are providing? Now see, we are providing 3 bars, 3 into pi by 4, 25 square. Area of 1 bar. 3 into area of 1 bar. So total 1473 mm square. Required is how much? 1410 is required. And how much we are providing? 3 bars means it is 1473. More than that required. Okay, fine. Okay. So next step is check for shear reinforcement. As usual in the previous problem, same step we will going to follow. That is, we have to check whether the stirrups are required or not. Okay. So first we will calculate nominal shear stress. That is tau V. Nominal shear stress tau V is equal to VU upon BD. Okay. VU upon BD. So VU shear force, total shear force 123 kilonewton. Multiply by 1000, it is Newton. Okay. So VU divided by BW into D. Again B means BW. So only in this while calculating the percentage of steel, we have to substitute BF. Okay, you have to substitute BF. Otherwise, in all the formulas, it is BW only. Remember. So VU upon BW into D. BW is width of web 300. Effective depth is 500. So nominal shear stress tau V is 0.82 Newton per mm square. 0.82 Newton per mm square. So it comes out 0.82 Newton per mm square will be the nominal shear stress. Then what is the permissible tau C? We have to calculate. But for calculation of tau C, first percentage of steel. Already this is calculated. Shear. Right. So what is the percentage of steel we are providing? PT is equal to AST upon BD into 100. Okay. AST upon BD into 100. So AST is this providing 1473 divided by BW into D into 100. 0.98. So now go back to the table number 19 now. Okay. Table number 19, IS 456 2000, page number 73. Go to the page number 73. Okay. Refer table number 19 for the value of 0.98%. First column is this PT only, 0.98, where AST upon B into 100 is given. So for 0.98%, what will be the tau C value? Tau C value is 0.60 Newton per mm square. This is permissible. It is called as permissible shear stress or design shear strength of concrete. Design shear strength of concrete. Now see, compare tau V and tau C. Now compare tau V and tau C. Nominal shear stress is 0.82. But how much maximum shear stress taken by the concrete is this. So since tau V is greater than tau C. Okay. Since tau V is greater than tau C, shear reinforcement is required. Remember, this is important stuff. Okay. Since tau V is greater than tau C, okay, the shear reinforcement will be required in the form of stirrups. So therefore, now we are going to design the shear reinforcement, that is in the form of stirrups. Now what is the total shear force? The total shear force VU equal to 123 into 10 raised to 3 Newton. This is the total shear force coming on the beam. So out of this total shear force, some amount of shear force will be taken by concrete. Okay. Out of total shear force, some amount of shear force will be taken by concrete. How much concrete will going to take shear force? Tau C into BD. Okay. So that is tau C into B means BW into D. So tau C is 0.6 into BW is 300 into D is 500. Okay. So total, that is shear force taken by the concrete is 90 into 10 raised to 3 Newton. See, out of this total 123 into 10 raised to 3, how much concrete will going to take? 90 into 10 raised to 3 Newton. So remaining who will going to take? The remaining shear force will be taken by stirrups. Now for that we have to design the stirrups. Okay. Now what is the balance now? Balance shear force to be taken by stirrups, that is VUS. VU means shear force taken by the stirrups S. VUS is equal to total shear force VU minus shear force taken by the concrete. So that is 123 into 10 raised to 3 minus 90 into 10 raised to 3. So this is 33 kilonewton, or 33 into 10 raised to 3 Newton divided by 1000, that is 33 kilonewton. So this, for this shear force, to take this shear force, we have to design the stirrups. Now directly you can assume the diameter now. As you have known in the previous case also, assume 8 mm or 10 mm diameter bars for the stirrups. So assuming 8 mm diameter, two-legged stirrups, okay, two-legged stirrups, 8 mm diameter for the stirrups. What is the spacing now? So spacing is equal to, this is the formula again there in the code book, 0.87 Fy ASV D divided by VUS. This is not AST. Remember, this is ASV divided by VUS. That is 0.87 Fy ASV, that is area of stirrups, two-legged. We have multiplied 2. This 2 is because of two-legged. 2 into area of 1 bar. What diameter we have assumed for the stirrups? Pi by 4 8 square. This is two-legged. So 2 into pi by 4 8 square into effective depth 500 divided by shear force taken by the stirrups, this VUS, that is 33. It is new into 1000 Newton. Okay. So therefore spacing is comes out 547 mm. So directly don't provide this spacing. Spacing means center of one stirrups to the center of another stirrups. There are 3 criteria we have to consider. But spacing of stirrups should be least of the following. Least. Okay, lesser value of the 3 values. One is this, that is SV spacing is equal to 547 mm. Then second, SV spacing is equal to 0.75 into D. 0.75 into effective depth of the beam, that is 500 mm. 0.75 into 500, that is 375 mm. Then spacing 300 mm. So out of these 3 values, which is least? 300. So that will be your spacing. So finally you can write down, provide 8 mm diameter. Okay, we have assumed 8 mm diameter, two-legged stirrups. Okay, we have assumed two-legged, 8 mm diameter, two-legged stirrups at a spacing of 300 mm center to center. Okay, as a shear reinforcement throughout the length of the beam. So what is the length of the beam? 8 meter. So throughout the 8 meter at spacing of 300 mm center to center, we have to provide 8 mm rings. Stirrups is nothing but it is a link, rings. Okay, two-legged stirrups are provided. So this is design of shear reinforcement. Next is deflection check. We have to check the deflection. Whatever the cross-sectional dimensions we have provided, whether these dimensions are able to take the deflection, whether the deflection is within the permissible limit or no, you have to check. Okay, that is check for deflection control. As usual, the same steps will be followed. First you have to calculate L by D maximum. So how will calculate L by D maximum? L by D maximum is equal to L by D basic into KT, that is modification factor for tension reinforcement, KC modification factor for doubly reinforced, that is compression reinforcement, and KF is modification factor for T-beam, flanged beams. So here KC is 1. Okay, KC is equal to 1 only because it is not a doubly reinforced beam. At top, no compression reinforcement is there. So directly you can take this KC is 1. We have to calculate KT and KF. So what is the percentage of for KT? What is the percentage of tension reinforcement? 0.98. Already we have calculated this. Okay, again go back to the IS 456 code book, figure number 4. Okay, you are going to refer figure number 4, page number 38. Okay, remember this, page number 38, figure number 4. For this 0.98%, what is the KT value? KT value is 2. Okay, figure number 4. Okay, refer KT value is 2. Then similarly, figure number 6, Figure number 6 for KF value. Figure number 6, page number 39. Okay, KF value. So again, in that directly, first calculate BW by BF, x-axis, this is x-axis there. BW by BF, it is 0.118. BW, width of web, divided by BF, okay, 2530. So it is 0.118. So for this 0.118, what is the y-axis? Y-axis is nothing but KF. So 0.80. So KC is 1 now. So substitute here, L by D maximum is equal to L by D basic into KT into KC into KF. Okay, that is equal to L by D basic. So normal L by D basic is 20, but for T beams this 20 will be multiplied KF is 0.8. So it is 16. So this L by D basic is 16 into KC is 1 into KF is 0.8. So L by D's maximum comes out 25.6. Ratio it is. Effective span divided by effective depth ratio is 25.6. Now actually how much we are providing now? L by D actual or L by D provided. So how much L? Span 8 meter or 8000 mm divided by effective depth is 500 mm. So this is 16. L by D is 16. Actually we are providing 16, but how much maximum allowed? 25.6. So it is anyhow less than this. Okay, so write down, since L by D actual, this is L by D actual is less than L by D maximum. Okay, so automatically the deflection is within the limit, or you can say that the deflection control is satisfied. There is no necessity of revising the problem. Suppose if L by D maximum, if it is more than this L by D provided, then you have to redesign from the first step. Okay, so anyhow L by D actually is less than L by D maximum, deflection is within the control. Last you have to sketch the reinforcement. This is the longitudinal section. Okay, now bottom main steel, how much? 3 bars we have provided, 3 bars of 25 mm diameter as main steel. Top, this is what you are seeing, hanger bars. Directly you can write 2 bars of 12 mm diameter as hanger bars or anchor bars. Then these are the stirrups what you have designed. So stirrups are 8 mm diameter, 2-legged at 300 mm center to center. Okay, 300 mm center, one from one stirrup to another stirrup. This is a spacing 300 mm center to center. So if you see the cross section, this is the slab now, this is the BF. Okay, then this is the beam. See, if you cut here, if you see from the this side, if you see this side, this will going to see, this is a slab, this is the beam, this is overall depth from this to top of the bottom of the beam. Here these 3 bars, here these 2 bars, and this is the stirrups. This whatever you are seeing, this is the stirrup. So bottom 3 bars, top these 2 are anchor bars or hanger bars, and this is stirrups. So this is cross section, this is longitudinal section. So this is the design of, okay, flanged beam, that is T beam. So just smaller changes will be there compared to the singly reinforced beam. Okay, so I hope you understood this problem. So my humble request is solve all these problems, that is design of singly reinforced beam, design of doubly reinforced beam, design of T beam. So out of this, in module number 3, okay, in module number 3, one full problem you will going to get in the examination, full 20 marks design problem. Okay, either design of singly reinforced beam, or design of doubly reinforced beam, or design of this T beam. So my kind request is solve once again all these 3 designs. Okay, if any doubts are there, you can call me, right, and ask your doubts, clarify your doubts. Okay, so thank you very much for attending this session. So next one more design is there, that is a cantilever beam. In this only we have seen simply supported beam now. So suppose if the cantilever beam is there, how to design that in the next class we are going to see. That is the last design in this module number 3. Okay, so thank you very much for attending this session. Okay, so once again I wish you all a very happy new year. Okay, thank you.